And so today we're going to cover lesson 7 from the energy unit, natural causes of climate change. So to start with, what is climate? Well, you know from your day-to-day experience about weather already. So weather is variables like temperature, humidity, that is like how much water there is in the air, precipitation. These are all things that we maybe want to know about, is whether they're going to happen on the weekend. And you'll usually as well attach those to a particular place. Climate is a little bit different, although it's a similar concept. With climate, we're talking about long-term patterns, that are long-term in the weather. So a climatologist, someone who studies climate, will be more interested in questions like, what is the average temperature at this location? How does it change on a day-to-day or year-to-year basis? More, I guess, the year-to-year. What are the patterns in the climate and the different variables for a whole region over the course of the time? Climatologists are interested in the big picture rather than just wanting to know whether you can go camping on the weekend. So that's a distinction to me made right there. So if you ever hear of it's going to be a really, a really cold weekend in the summer or something like that, and then someone says, well, that's about it for climate change, I guess that's not, it's not happening. Well, what they're talking about then is an event in the weather. Yes, there will be decreases in temperature on an occasional basis. Climate change is about average changes in climate over a long-term period, over a large area. So today we're looking not at man-made, human-caused climate change, but at climate change in general. Now, what we can see from this diagram right here, this picture right here, is an example of how people have mapped climate change in the past. I mean, obviously, 600 years ago, there weren't weather satellites, and there weren't people with thermometers recording the temperature all over the course of over the span of the world. It just wasn't happening. Does that mean you can't study the climate for that time? No, you can. What you use are what are called proxy measurements. So a proxy measurement is it's a measurement of climate where you're measuring something that correlates with climate variables. So and correlating means that the two variables are related. For example, right here we see a tree. It's this tree that's been cut down. It was really old. So what I want you to notice is the tree rings. Each tree ring records the tree's growth over the course of 1 year. And we see that for this period right here, about 500 years ago, we see a long-term period, I don't know, several decades certainly, where the rings are really close together. Trees are very responsive to differences in temperature, and especially to increases and decreases in rain, precipitation. When you don't get enough of it, the tree won't grow very much. So these kinds of long-term patterns can be recorded in the rings of a tree. Now, when you're doing a study like this, of course, you're not just looking at the width of the rings of just one tree. What they would do is they're going to get trees that live for a long time, like bristlecone pines, and which can live over 3,000 years, and they're going to get a series of tree rings from bristlecone pines or a tree like that, and then they're going to map out the temperature changes or precipitation changes over the course of thousands of years. So that's a little bit about using proxy measurements. Now you might think, well, okay, how far can we go back with that? Well, what actually has been able to happen with this study, which is called dendrochronology, is people have been able to find old trees that have fallen a long time ago and kind of map out the overlap of the rings from several trees that didn't fall recently but that died a long time ago. And they've actually been able to use this study of tree rings to go back something like 9,000 years. So dendrochronology, using that kind of an overlapping method, is a long-term study, and it, among other things, has shown fluctuations in climate, like in temperature and precipitation, that match well with others like using, for example, pollen and ocean sediments. Something that is very important, is often used for measuring and projecting temperature over time, have been ice cores. So what's done with this is people go to a part of the world like Greenland or Antarctica where there is an ice cap that might be, say, thousands of feet deep. And they will cut a core from that ice where they know how old each level is in the core. And then what they can do is they can get trapped bubbles of air from the ice and record information about the chemistry of those air bubbles. Mostly what they're looking at is what's called the oxygen ratio, like how much of there is there of oxygen 18 versus how much of oxygen 16. If you guys did the isotope worksheet, you'll know what I mean, the nuclear reactions worksheet. The ratio of the two tells you information about temperature changes in the ocean over time, the ocean that's close to Greenland where the snow falls for that. And these sorts of measurements can also be repeated for ice cores in different parts of the world, like in the mountains and in Antarctica. So these ice cores actually allow temperature to be measured back in Greenland some thousands of years, in Antarctica I think it's some tens of thousands or hundreds of thousands of years. There's very old ice in Antarctica. Now, of course, when you do this, again, you don't just take one core, you take several cores, and you get a collective story from the cores that you find across a large area, like is shown in this study right here. Now, what have they found? Here is a diagram of what they found for temperature over in Greenland for the past 12,000 years. So if you look 12,000 years ago, let's start right there, it was a lot colder because they were in the middle of an ice age, some 9 degrees colder than it is right now, about 12,000 years ago. There was a rapid temperature increase as the ice age came to an end, and there was a period about 4,000 years after, 3,000 years after the ice ages ended, which was actually warmer than it is even today. But then what we see is an overall drop in temperatures until around 100 years ago, or actually, about 150 years ago, when the temperatures start to increase again. What's going on right here actually is for the last 20 years, not there, but for the last 20 years, they've actually used temperatures from other methods, and they kind of like stuck the data together. That's a bit problematic doing that, but there is also debated and sound science behind doing it. What's been found is that temperature spike shows up where, temperatures were kind of on a decreasing trend before the industrial era, but then they've all of a sudden spiked back up. The concern, of course, is if they keep spiking up over this century, and the worry is that we might see temperatures well above what they were here. In fact, temperatures that might be as high as they've ever been in 200,000 years. So temperatures fluctuate because of a natural means for a lot of reasons. One I wanted to go through really quickly is this. There's obviously climate change over the course of just one year, and it follows yearly cycles. Some people, it's a common misconception that the seasons are caused by changes in difference between the Earth and the Sun. Anyone who's in Australia on June 21st will know that that doesn't make any sense because on June 21st in Australia, while we have summer, they have winter. In other words, we have to look for some other explanation. The explanation is the fact that the Earth orbits on a permanent tilt. It's always facing the same part of outer space, and the tilt of the Earth is not perpendicular to the orbital plane. What does that mean? Well, it means that for part of the year, the North Pole, over the course of an entire day, is facing away from the sun, and the South Pole is facing towards it. And then it switches 6 months later. Look at this, January 6th. On January 6th, the North Pole is facing away. Right here we have the the Arctic Circle. And then here's the Tropic of Capricorn, or excuse me, Cancer, and the equator right there. Of course, the Earth is rotating on this kind of an axis. As it does that, the sun's never rising in the north and never setting in the south. When you're at the Arctic Circle on December 21st, the sun will just peak above the horizon and then set, right? Peaks above the horizon here, the Earth rotates, and it's nighttime again. You get, when you're at the Arctic Circle on on January 6th, you just see a peak of the sun just for a moment. So, and I've lived that, of course. I lived in the Arctic, and I can tell you, when the sun rose again on January 4th after 2 weeks of complete darkness in Nunavut, it was very exciting, and I and all my students crowded to the window to see the sun even just for a half hour. So this explains the seasons. The other thing I'd like you to notice about this is watch the values in temperature, watch the values in light intensity at the equator and compare them with the values at the Arctic overall. What's the maximum reaches the equator? What's the maximum it reaches at the Arctic? Okay, so here we see the equator. I guess by definition it's reaching 100. And at the Arctic Circle, it's never reaching more than, I think, 70. Let's have a look. Okay, 73 is where where you get that maximum value. What's going on there is that it's to do with the angle of light. We see at the equator that the angle of light of the sunlight's relative to you varies between 90. In other words, the sun is light shining directly down the top of your head, down to a minimum of 67. That's not a huge amount of variation. Versus here in the Arctic, the Arctic Circle, we're going from 0 up to 46. This has huge impacts. It means that given amount of sunlight in the Arctic is spread over a much wider area. So, yeah, the same amount of sunlight reaches these parts of the world, but it's when it reaches this part of the world, a unit of sunlight gets spread over a bigger area. It has to, and as a result of being spread more widely, it doesn't heat the Earth's surface as much as the sun in the equator, where it's shared over less of a surface area. So this explains that difference in the angle at the Arctic Circle versus at the equator, explains this difference that we're seeing in overall temperatures. It's hotter at the equator, although I said in my last lesson that from the equator we have Hadley cells, we got low pressure at the equator, air rises, moist air rises from the equator, warm moist air rises from the equator and is pushed away from the equator, and by the Coriolis effect it spirals off and creates weather systems in the temperate latitudes. What's going on, in other words, is because through convection temperatures are continuously being redistributed across the surface of the Earth, but the Coriolis effect kind of slows it down and makes these spinning weather systems. I hope you watch that video. There's a lot of detail to it that I don't want to explain only right now. So this is a season simulator for the course of a year. We've already seen that. Next, I would like us to look, I'm not going to look at composition of the atmosphere right now. I'm actually going to look at that at the end of the lesson. In fact, I'm just going to touch on this really quickly. I did tell you in the last lesson I talked about the water cycle. I just want to remind you that this also affects the climate. It affects the climate on a local basis. Areas of the Earth's surface that are closer to large water bodies have a more moderate climate. The high heat capacity of water means that water stores a lot of thermal energy, and that influences the climate of places close to the water. When you're close to the water, it never gets so very hot, and it never gets so very cold. Also, temperate water with its high heat capacity, when it's moved inland, that in itself is also going to be affecting the surface temperature of places where the water falls. You get more moderate temperatures close by because of water being transported to these places. So that's a little bit for you about the water cycle. I do as well want to go into this whole topic of ocean currents. Let's close this off, and this too. All right, now what we see right here is a diagram of the ocean currents. In fact, let's just go back to this for right now. I'll show you this more later. Remember that the little lines on here correspond to winds at the surface, okay? And I'm going to show you more about this globe a little bit later. The winds at the surface of the ocean here are moving from east to west. This is because of the Coriolis effect. Hot air rises right here, is pushed north, but it is twisted towards the right as it does that, and then it comes back here and going south. Again, it's twisted towards the right, and the overall movement at the equator is of air going in that direction. What that does is it also affects what happens to the surface ocean currents. If the wind is moving in this direction, the water beneath it at the surface of the ocean is going to do the same thing. So we see ocean currents in the Pacific, at least, are moving from east to west. There are different patterns that occur in other parts of the world because weather is complicated. What we see seasonally in the Indian Ocean, in fact, is the opposite, and this is due to the proximity of this ocean right here to so much land and the uneven heating of the land versus the water. I'm not going to get into that right now. Notice this is going to go again for this in the same way as the Pacific. So this here is due more to what's going on in the hot Africa and India, uneven heating of the Earth's surface. That you're seeing in the Indian Ocean causes what are called the monsoons. If we focus on what's going on in the Pacific, that is regulated by the Coriolis effect, we see water moving from the east to the west. Now, water temperature has a really big effect on land temperature. So imagine the conditions, say, right here, right off the coast of northern Peru. What you find there is that given that we're in the tropics, it's unusually cool. The water off the coast here is unusually cool considering where you are in your latitude relative to the equator. So you find in these coastal areas of South America, certainly down in southern Chile and southern Peru and Chile, northern Chile, the water off the coast is really cold. This also has to do with high pressure zones, high pressure, dry, cool air that comes down here, and it also has to do with ocean currents. When the water's cold off the shore, even if you're in a tropical area, you can't have as much evaporation, and so you don't get that moderating influence. You don't get a lot of rain, but you also get colder temperatures at the shore of the ocean. So here, even though we're in a kind of tropical area, at the shore of the ocean, at these coastlines here, it's very dry. Versus if we see what's going here, we've got ocean currents in the Pacific that are moving from the east to the west in that kind of flow that results from the Coriolis effect. So that's the Coriolis effect for you as it's affecting the ocean currents. How does that relate to climate? Well, what does happen sometimes is that these winds here, right here, it's not like they can't change ever. There are many factors that affect the climate. And if the winds that move this water from east to west, if they start to die off, then water here in the Western Pacific can make its way towards the western coast of South America. When it does that, when you get unusually warm blotches of water off the coast of western South America, that's called the El Nino. The opposite of is La Nina, when it gets even colder off here. And what has been found is that these kind of temperature events at the Earth's surface, SST means sea surface temperature, they start to have knock-on effects on the climate in other parts of the world. Sometimes you'll hear, oh yeah, it's an El Nino year. What that means is that we've got warm water off western Peru. What that does is it causes warm winters in North America. So that's an example of a climate phenomenon that it's natural, although at the same time greenhouse gas emissions have had effects on the El Nino. So that's ocean currents. I also did want to show you, here it is, good. I'm going to also recommend you watch this video about ocean currents. So this is another natural phenomenon that, however, could be affected by human-caused climate change. So what we see right here are ocean currents at the surface, but also ocean currents deep in the ocean. The blue currents are ocean currents at the surface. The red currents are ocean currents at the surface. The blue ones are deep ocean currents. So I had a great image about this I wanted to show you. Forget it. All right, here's the deal. Notice that these ocean currents, the one current can go over the other. This is because this one's going on top of this one. The arrow shows which way it's going. So if we see in this part of the Atlantic, we've got ocean currents at the surface going from east to west. They go through the Caribbean, and as they go across the Atlantic, what's happening here is heat is being released into the atmosphere. It actually makes it warmer in this part of the northern Atlantic than it would be otherwise. But what happens right here is that by the time it's reached this point here, this is called the Gulf Stream, the water has sapped off its energy, it's released its energy, it's got really cold, and colder water is more dense, and so it wants to sink. In addition, it's cold, yes, but having lost a lot of its water by evaporation as it went across the warm Atlantic, it's salty. So cold, salty water happens to be more dense than water that is warm and not so salty. Here, I'm going to show you the picture. Here it is. Did a little experiment on this for my Science 9 students, and here's what we found. Here, I mixed, I put cold water, I put salty, this here is salty water, and this is non-salty water. I found that when I put salty water at the bottom, I was able to pour non-salty water on top of it, and it just sat there. Versus if I poured salty water into non-salty water, they mixed. Here I did the same thing with hot versus cold water. In this case here, I poured cold water at the bottom. I was able to get hot water to stay on the top of it. Here I put hot water on the bottom, and when I poured cold water, they mixed. So this shows you that when you have cold water on the surface, it sinks and mixes. When you have salty water at the surface, it sinks and mixes. This explains this pattern right here, where we've got this water that sinks, and when it then sinks, it flows underneath the water. The surface currents, as you can see from this, are relatively fast. These currents here, oops, where'd it go? These currents right here are much slower. This is called the Great Ocean Conveyor Belt. It might take a molecule of water 1,000 years to make this trip. The surface parts of the trip are a lot faster. So, whereas the deep ocean currents, they carry a much larger body of water, just moving a lot more slowly. So that's the Great Ocean Conveyor Belt, and as you could well imagine, it also has effects on temperature, right? If the water is warm, it's going to have a warming effect on the land that surrounds it. If the water off the coast is cold, it's going to make the temperature at the coast on the land colder because of the high heat capacity of water. The other thing that I wanted to mention as well is this right here. This is just something you've probably heard of. You probably know that, hey, the dinosaurs are extinct except for birds. Why did that happen? Because of a giant asteroid striking the surface of the Earth. So what went on? This was about 65 million years ago. A rock somewhere between 8 and 10 kilometers in diameter struck southern Mexico. Here we go. Bam. hit around the Yucatan Peninsula, and massive ball of fire, destroyed forests. Anyways, eventually killed the dinosaurs. This was not only due just to fire, by the way. What's actually thought to be the bigger issue is not fire, and not the tidal wave, although the tidal wave from that would have been immense. That would have affected mostly just North America. The big issue was what are called aerosols. Aerosols are also called particulates, are substances that they're like smoke, little bits of dust that get into the air. What happens with aerosols is that when they get into the air, they cool down the climates. This is a global map of aerosol concentrations. In other words, stuff like smoke in the air. Where aerosol concentrations are higher, they tend to reflect the radiation from the sun, and that leads to the radiation from the sun reflecting back into space. When the Chicxulub crater was made by that giant asteroid or meteorite hitting the Earth, that kicked a lot of dust into the atmosphere, and the sun's rays, they were trying to reach the surface of the Earth, quote unquote trying, but they were reflecting back. It would have led to a winter several years long. Really big animals with high energy needs couldn't survive those conditions, and so the largest animals on Earth at the time, the dinosaurs, died off. Not too long after that, some tens of millions of years later, I think 5 million years later, even they started to be replaced by giant mammals, which lived up until humans started hunting them. So that's an influence of particulates that results from catastrophic events. But those are the natural things I wanted to describe to you, natural and also human influenced. Oh, darn. The other one, though, is the carbon cycle and atmospheric composition, which you see is like the first point in that table. Let's get back to this. Where was the one I wanted to show you? I think it was this one. Maybe, yes, it was. So you know that carbon dioxide is a greenhouse gas. Okay. I want to get into that a little bit more. First of all, where does carbon dioxide come from in the atmosphere? Will come from in general. The pools of carbon in the Earth in general are the atmosphere, also water, vegetation, and fossil fuels. These move through a cycle that is not just one single cycle. There's actually several cycles within it. There's a lot of carbon locked up as carbon compounds in oil and gas. When we burn those, we release carbon dioxide into the atmosphere. But it doesn't end there. That carbon dioxide can then dissolve in water. When you have soda water, you're drinking water with carbon dioxide dissolved into it. Some of that carbon dioxide within the ocean or fresh water is taken up by marine plants, which are then eventually eaten by marine animals. Some of those marine plants also, however, sink into the sediments and they end up in limestone and in coral, but some of that as well ends up back in fossil fuels. But the cycle doesn't end there. Some of the carbon dioxide from the atmosphere ends up in the soil as dead plant matter, or it ends up in vegetation and in other living things on the surface. And that's what's called another kind of carbon pool. So the carbon cycle is not just one circle, but several cycles or several circles within it. It's a complicated system, but the bigger picture for you guys to know is that carbon dioxide is one of several greenhouse gases. So I was looking into this a lot more, and I started to get interested in looking at what is a greenhouse gas and why are there greenhouse gases and how do they work. First of all, I'd like you to notice that this is another example of that null school map, all right? And it actually tells a story about carbon dioxide in the atmosphere. watch this here. First thing I'd like you to notice is I'm going to find a place where there's very low carbon dioxide in the atmosphere. Okay, right here, 411. The first thing I want you to notice is this, and I'll get back to it more later. It's that number, 411. If you look at web page articles from, say, the year 2000, you find people saying, wow, carbon dioxide levels are nearly at 400 parts per million. It hasn't been like that for 800,000 years. And they were panicking. And it's good that they were panicking because they should. Now it's virtually impossible to find anywhere on Earth where concentrations are below 400. At this point in time, they're going above 430. Let's see, 430 in Hawaii. And if we look right here, 434. What's going on? Why are the carbon dioxide concentrations so uneven? Well, one factor that's going on would certainly be industry, but is there a lot of industry here in northern Siberia? Maybe, no, not a whole lot. What's going on at the time of I'm making this video, this is early June, photosynthesis in the north is only just kicking up, but decomposition's been going along all through the fall and into the spring. So as a result of that, carbon dioxide's being released right now in northern Siberia and in northern Canada before the plant growth has had a chance to catch up. What will eventually happen is CO2 concentrations will start to go down in the green north of our world, just as they are down in parts of the world right now where there's lots of plant growth, like in the Amazon basin, the jungle of the Amazon basin, lots of forests, lots of photosynthesis, much lower carbon dioxide concentrations there. Now, I don't know this for sure, but I think what's going on here in eastern China is, well, they have massive amounts of industry there, and as a result, not surprising, there's going to be lots of carbon dioxide being released. One other gas that kind of relates to this indirectly is carbon monoxide, and check out carbon monoxide. Carbon monoxide is released, by incomplete combustion. For example, burning coal, burning natural gas, burning petroleum, some carbon monoxide gets released. Look where carbon monoxide concentrations are highest. Eastern China, Southern California to a small degree, India, the great industrial centers of the world and cities of the world are the major sources of carbon monoxide. There's another which is very disturbing I want you to look at. That is this right here. What's going on in the African basin? Let's check out maps. Should be good. All right. Well, this is the Congo basin right here. All right, that central part of Africa, that green heart of Africa is what it's called. But what's happening there? Here. Well, unfortunately, the bad news there is that the jungles are burning in the Amazon, but they're burning even worse in the Democratic Republic of Congo right now. This right here, to my mind, and I'm not an expert on the area, but we know that tropical rainforests are endangered across the world. The Amazon isn't the only place. To my mind, these high carbon monoxide concentrations come down to people clearing forests in the Congo basin as well as in the Amazon. So those are some gas concentrations in the atmosphere I wanted you to have a look at. And again, right here, we see these high concentrations here of carbon dioxide where there's not the photosynthesis yet happening. All right, but how is it that the greenhouse gases work at all? There's a great website I found called explainingclimatechange.ca. You might want to check it out. It has huge amounts of information, but what I really like is it's got some of these applets. Applets are little like apps that show you things. Right here is what's called an electrostatic potential map of carbon dioxide. The black in the middle, carbon. The reds, oxygen. Carbon dioxide, carbon and oxygen are very different elements, different chemical elements, and they have different abilities to pull electrons. Oxygen is way better at pulling electrons than carbon is. So what oxygen does is it pulls electrons away from carbon, and so the electrons are distributed unevenly over the surface of a carbon dioxide molecule. And the same is true for many other molecules in the atmosphere, like water, H2O, 2 hydrogens, 1 oxygen, and the nitrogen dioxide concentrations. We have these uneven distributions of electric charge across the molecule. This is not the case for oxygen gas, O2. It is not the case for nitrogen gas. And they're the majority of the atmosphere. But what are called the greenhouse gases have these uneven distributions of electrons across the surface of the molecule. What that does, the effect of that, is to make these gases able to absorb and re-emit infrared radiation or heat radiation. Where did I want to start? Right here. All right, we've seen that. First of all, I want to remind you, what do I mean by infrared radiation? That's not it. No, that's not it. This is it. Okay, here's the electromagnetic spectrum. You learned about this in grade 8. So you'll probably remember from grade 8 a little bit about optics that there's gamma rays, there's X-rays, there's UV, there's the light we can see, there's infrared, microwave, and radio. Infrared radiation is the radiation that makes you feel warm. If you say have a wood stove and you open up the wood stove when it's running and you put your hand out, you're not putting your hand on burning wood, I hope. But if you hold your hand up to towards the wood stove, your hand feels really warm, right? What that is radiation, infrared radiation, radiation that's invisible to you, but is coming from the wood stove and heats up your hand. Specifically, it's heating up mostly the water molecules that are the majority of your body's mass. Those molecules get excited because they can absorb and re-emit infrared radiation. They get really excited and they move around faster. And when they move around faster, that increases temperature. Water molecules are also in the atmosphere a greenhouse gas. They have this ability to absorb infrared radiation, get excited, to move faster. And when they move faster, they start to bump around other molecules like nitrogen gas in the atmosphere. This is what causes the greenhouse effect. It's these greenhouse gases. So the nitrogen gas and the oxygen gas in the atmosphere, they don't do this. If the atmosphere was just nitrogen and oxygen, we wouldn't have a greenhouse effect. It's because of these molecules that have that uneven distribution of electrons that makes our atmosphere get warmer from the sunlight. So just a reminder then, UV is like really high energy, low wavelength. This is the light we can see, but what's really of interest here is this infrared radiation that gives heat to things when they absorb it, when matter absorbs it, like water. The molecules get excited, they bump into other molecules, and the temperature goes up. Now, let's look at an example right here. Okay, this isn't, darn. Okay, I'm gonna have to start this one again. Okay. This is it. Good. Okay. This is a molecule that's made out of 1 carbon, 2 hydrogens, and 2 chlorines. The chlorines give it a really high, really uneven distribution of electrons. The little things zapping by are photons. Those are units of electromagnetic radiation. So here it's getting hit by, if it comes from here, it's getting hit by an X-ray. If it comes from here, it's getting hit by a photon that's infrared radiation, and so forth. This thing is kind of difficult to control. Let's see if I can make it work. Okay, there. So what just happened is a photon of infrared radiation hit it, and it made the molecule all excited. These bonds here are vibrating really fast because they have been hit by this photon. If you put it over here, other weird stuff can happen. The photon go over here, hits it, can cause one of the atoms to fly off, and you get a different molecule. But we don't have to worry about that right now. You do have to know that this is how greenhouse gases work. They get hit by infrared radiation, and the molecular bonds start to vibrate and get excited. An excited molecule can move faster and bump into other things that aren't greenhouse gases and cause an increase in temperature. Okay, we've seen that. Here, okay, this is it. Yes, okay. This here really tells the story, though. Here's the deal. What this graph will show right here is a graph of wavelengths of light. So when the sunlight hits the Earth, some of it just bounces back into space, but some of it is absorbed by the Earth and converted to infrared radiation. But then having absorbed it, it's going to re-release it, and it re-releases it back into space, some of it. Some of it that is re-released back into space, though, has the chance that it will be absorbed again by the atmosphere. That's the greenhouse effect. Now, only certain gases can do that. Nitrogen, oxygen can't, but these gases right here can. And each gas has its own absorption signature. So if these are wavelengths of infrared radiation, and I'm going to show you right here, this, for example, is water. This tells us that water absorbs infrared radiation here, and infrared radiation here at this frequency right here. So this is a chlorofluorocarbon. Here's where it has its absorption. Ozone, HCFC, carbon dioxide. So these corresponds to wavelengths where the carbon dioxide and these different greenhouse gases absorb infrared radiation and then can use it to increase atmospheric temperature. I'm going to close this and reopen it. I'm going to show it differently. Okay. This here is a diagram that shows the relative intensity of the Earth's emission spectrum. So the Earth does not, of the infrared radiation that the Earth radiates outwards, most of it's not this wavelength at this frequency. Most of it is around here. Okay, so the Earth is warmed up by the sun. Here's the kind of infrared radiation, the frequency, which relates to the wavelength of energy that the Earth re-radiates. Now, this is the awesome thing about this app. It can map the absorption spectra, the absorption wavelengths, I should say, of these molecules on top of the emission. So this is emission right here. Okay, the black line is emission. There. This line right here is reabsorption. So Earth is emitting this much. And if we didn't have greenhouse gases, all of this will go back into space. But because we have water in the atmosphere, it can reabsorb energy here and reabsorb energy here. Chlorofluorocarbons can do that, although they're not yet important enough to reabsorb much of what's re-released. Ozone has its effects here and here. HCFC does here. Methane, as well as greenhouse gas, because it's got uneven distribution of charge. This is another CFC molecule. Nitrogen dioxide, which is released as part of some air pollution. But the big one, for this purpose, is CO2. So wavelengths, when infrared radiation is re-released by the Earth at this frequency, carbon dioxide reabsorbs most of it. This is why carbon dioxide is such an important greenhouse gas. So that's what I want you to know about atmospheric composition. If there were none of these greenhouse gases, which one didn't I click? Whatever. If there were none of these greenhouse gases, then Earth would be emitting, oh, there it is, and Earth would just be re-emitting all this infrared radiation back into space. It absorbed it as visible light or other wavelengths. It became infrared radiation. It re-released that infrared radiation, like for example in the water that makes the Earth's surface, at the Earth's surface, absorbed it, made it into infrared radiation, re-released it back into space. If there were no greenhouse gases, describes the frequencies that will be re-released back into space. But because we have greenhouse gases in the atmosphere, like carbon dioxide, like water, some of that has a second chance. Some of that infrared radiation has a second chance to be absorbed. And what it does when it's absorbed by these greenhouse gases in the atmosphere is they excite the other gases next to them and cause an increase in temperature. So that's what I want you to know about the interactions, except collisional heating tool. I think this one's going to be working too. Okay, excellent. So there. What this is just really another way of showing is the different wavelengths, what happens to carbon dioxide when it gets hit by photons of different wavelengths. It's actually not what I wanted to show you. See if I can find it. Okay. All right. You know what? I'm not going to find it. Doesn't matter. So what I've shown you in this video is how the composition of the atmosphere, the greenhouse gas works, and with reference to the gases that are and are not important greenhouse gases and why. The greenhouse gases in the atmosphere are really important. If we didn't have them, then the atmosphere would be some 35 degrees colder on average than it happens to be. Showing you how the Earth's tilt and rotation affect the seasons, how the ocean currents redistribute thermal energy across the surface of the Earth, the El Nino and La Nina, how they vary from year to year, and how that affects climate over the course of the one year to the next, especially in North America, and then the very occasional but catastrophic effects of asteroids hitting Earth. So those are the natural causes of climate change I'd like you to be familiar with. What I'm going to deal with next will be human-caused climate change and how it's affecting you and me, and why it's more important to you than it is to me over the course of your lives, because it's going to be a big problem unless we tackle it seriously. I hope you found this lesson useful, and bye for now.